Hi guys, this is Dr. G here, and in this video we are going to talk about the effects of substituents on the electrophilic aromatic substitutions. Or in other words, when you already have a substituent on benzene, how is it going to impact the incoming electrophile? Okay, so that is what we are going to discuss in this particular video, and this is a very important video, so I highly recommend you to watch this video from start to end, and you should be able to understand a lot of good materials in this video. So for this particular lesson, we are going to need some of the keywords that we already know. Okay, so you might want to go through these keywords in detail by pausing the video if it is necessary, but I highly recommend that you guys understand all these keywords, excuse me. So let's talk about the background. So we are going to talk about the effect of substituents that are already present on benzene ring on the electrophilic aromatic substitution, right? So the first thing that you need to understand in this video is that you should be comfortable in electrophilic aromatic substitution. This electrophilic aromatic substitution reaction is a two-step reaction. Okay, so in this reaction, what you are going to do is you are going to substitute one of the hydrogens on benzene. You are going to substitute one of the hydrogens on benzene with an electrophile. So this is what you are going to achieve in this reaction, right? So this electrophilic aromatic substitution, where the substitution of hydrogen with an electrophile occurs in two steps. In the first step, of course, you are going to add an electrophile to the benzene ring. Okay, so in the first step, you are going to add an electrophile into the benzene ring. So this addition of an electron in the first step is unfavorable. Why? Because this addition will result in a loss of aromaticity on the benzene ring and the formation of a uranium ion. Okay, so this ion is unstable as compared to the aromatic benzene ring, mainly because it is losing the aromaticity and it is getting a positive charge on the benzene ring. So because of those reasons, this uranium ion is unstable and it can undergoes a few resonance structures and it can partially stabilize the structure of this intermediate. Okay, so these are the resonance structures possible. Okay, only thing that will change is the electrophile. Okay, so I think you're already familiar with how to draw these resonance structures. And in the second step, what happens is that this uranium ion will regenerate the aromaticity by using the carbon hydrogen bond electrons to generate the aromatic ring. Okay, so basically a base or whatever the base that is present in this reaction will attack the hydrogen and the two electrons will be used to regenerate the aromaticity on benzene. So this is the second step, and this second step is actually much faster than the first step. Okay, much faster than this first step. All right, so this is the summary of electrophilic aromatic substitution. So if you need more details, I would recommend that you guys go back and watch the video or the lesson on electrophilic aromatic substitution. So in this next slide, I have a detailed explanation on how the already existing substituents affect these incoming substitution. Okay, so basically when you already have a substituent present on benzene, let's call it X. So this is the already existing substituent. When you already have a substituent and here is the incoming electrophile, let's say, two things can be impacted. Okay, so this substitution reaction, the electrophilic substitution reaction, could be fast or slow. Okay, so of course it can impact the rate. Okay, so it can impact the rate. Okay, so this X, this already existing substituent X, can impact the rate of the reaction, and also it can impact the orientation. It can impact the orientation, which means it can direct this incoming group to a ortho, para, or meta position. It can direct it to an ortho position, to a para position, or even to a meta position. So basically, X can do two things. It can impact the rate of the reaction, or it can determine the site of attack, or we can say orientation. Okay, so based on these two things, okay, the electrophilic substituent effect can vary. Okay, so based on reactivity and orientation, there are three classes of substituents. Okay, so aromatic substituents that are already present on the benzene could be divided into three primary categories. The first category is called orthopara director and activator. Okay, which means the first category will basically direct the incoming group into an ortho position. Okay, this is ortho, or this is para. Okay, it can direct the incoming electrophile to an ortho or para position, and also it can increase the rate. Okay, so if the rate is increasing, we call it activator. Okay, and the second kind is also an ortho para director, so the incoming group will go either to an ortho or a para position, but it's a deactivator. It is a deactivator. Why is it a deactivator? Because it is decreasing the rate of reaction. And the third kind is called meta directors. Okay, third kind is called meta directors, which means the already existing substituent will direct the incoming electrophile towards a meta position. And meta directors are always deactivators. Keep that in mind. All right, next up is the classification of the already existing substituents on benzene. Okay, so we are going to classify the pre-existing substituent on benzene as orthopara directors or meta directors. Okay, so for that reason, I'm going to use a table. So in this table, orthopara directors are listed in the left hand side, and meta directors are listed in the right hand side. So here's the thing. For the exam, I could use any one of these substituents, okay, on any one of these substituents, and I will ask you where the new electrophile is going to be attached and whether it's an activator or a deactivator. So one thing you could do is you can try to memorize this table. Okay, most people do that, and most people become very successful in memorizing this table. Or you can try to understand this table. Okay, that is the more preferred method. If you try to understand this table, you don't have to worry about anything. I can throw you a curveball. I might give you a substituent that you have never seen before. Okay, but still, if you understand this table, you can figure out whether it's an orthopara director or a meta director, and then answer the questions. All right, so so if you want to understand this table, the most important thing that you want to remember is that meta directors are usually highly electron withdrawing. So meta directors are usually electron withdrawing groups. And one of the very common features of electron withdrawing groups is that if you consider the atom that is directly attached to the benzene ring. Okay, so this is the atom that is directly attached to the benzene ring. That atom usually have multiple bonds. That means double or triple bonds to another atom. Okay, so whenever you have the directly attached atom with multiple bonds to another atom, that could be a meta director. That is how I used to remember when I was studying this meta directors. So you worry about the first atom that is directly attached to the benzene. Okay, so in cyanide it is carbon, so sulfur, carbon, 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 nitrogen, nitrogen, carbon and carbon. So these are the atoms that are directly attached to benzene. Okay, so typically meta directors, for meta directors, that atom that is directly attached to benzene has double or triple bonds. Okay, double or triple bonds, or you can say pi bonds with another atom. Okay, so you have multiple bonds coming from that directly attached atom. So that is one way to remember it. And also there are exceptions, of course. Okay, I mean, this is one way to remember them, but there are exceptions. Okay, common exceptions are what? CF3, okay, CF3 and CCl3. Okay, these are common exceptions. And of course ammonium ions. Okay, so these are common exceptions. And the thing about these exceptions is that even though they don't have multiple bonds, okay, even though they don't have multiple bonds like the other electron withdrawing groups, okay, they are highly electron withdrawing. Okay, they are highly electron withdrawing. So they are highly electron withdrawing. So either they will have multiple bonds like these, or they might have highly electronegative atoms attached to the immediate carbon, like, you know, CF3. Okay, so fluorine is a extremely electronegative atom, the most electronegative atom in the periodic table. So therefore this CF3 is highly electron withdrawing. All right, so that is how you remember meta directors. So let's look at the structure of some of these meta directors in a little bit more detail. All right, so these are some of the commonly found meta directors, and as you can see, the atom that is directly attached to the benzene ring, it has multiple bonds. See, it has multiple bonds. Okay, it has double or triple bonds attached. So that is one way of identifying electron withdrawing groups or meta directors. And meta directors are always deactivators. That means if you have one of these grouped already present on benzene, it will try to discourage benzene from getting another electrophile. These meta directors try to discourage benzene from getting another electrophile. Why? Because as I mentioned earlier, these meta directors are highly electron withdrawing, so they basically pull electrons back. Okay, so whenever you have a meta director attached to benzene, they are pulling electrons from benzene. So benzene thinks that it is rich in electrons. Why? Because it has 3 pi bonds or 6 pi electrons. So benzene thinks that it is rich in electrons. Okay, but I mean, when you are rich in electrons, I mean, you think that, okay, I might be able to, like, you know, donate my electrons and get an electrophile, a homeless guy, right? So I might, since I have like more houses, let's say you are very rich, you have multiple houses, you know, closed down, you feel like, you know, you want to donate to charity, right? So you might invite a homeless guy to one of your houses and then let them stay in that house, right? So that is exactly what benzene does. If benzene is rich, benzene will basically get an electrophile. Electrophiles are electron deficient, but still it will accommodate an electrophile. But let's say benzene has a very expensive wife. That means, you know, benzene has an electron withdrawing group or a meta director on benzene. So whenever benzene has a very expensive wife, I mean, that wife is spending so much money, right? So benzene is no longer feeling rich. So whenever he wants to spend money on something, he's like, okay, let me think about it twice. Can I do this, right? So benzene will think against attacking an electrophile. Why? Because benzene is no longer rich in electrons because of the attraction of electrons towards the meta director. Okay, so it will no longer try to attack the electrophile. So that is why always the meta directors are deactivators. They don't want benzene to get any more groups. Okay, they feel benzene so poor. Okay, so you understand now. The story for this story for orthopara directors are a little bit different. Why? Because orthopara directors could be activating or deactivating. Okay, so if the orthopara directors are activators, Okay, if the orthopara directors are activators, that means they help benzene get an electrophile, an electron deficient species. So if an already existing substituent makes benzene more rich, that means that substituent is donating electrons onto benzene, right? So usually these activators, orthopara directors and activators, are usually electron donating. Okay, they are electron donating. They donate electrons towards benzene. Benzene is already rich in electrons, and these substituents are pushing electrons onto benzene. So benzene is like, hey, now I have more electrons so that I can easily attack an electron deficient electrophile. That is exactly how it happens. Okay, sometimes you can have substituents or orthopara directors that are deactivating. So usually these deactivators reduce the electron density on benzene. So therefore benzene will think twice before substituting an electrophile. Okay, so that is how it happens. All right, so if you understand that story, you should be fine. I mean, you should be able to easily understand the substituent effect on electrophilic aromatic substitution reactions. So in this slide, what we are going to do is we are going to take an example and then try to understand this substituent effect in more detail. Okay, so in here I have an aniline. Okay, so you have a NH2 group. You have an NH2 group directly attached to benzene. So if you remember the previous table, okay, if you remember the previous table, NH2 is what? NH2 is an strongly activating group. NH2 is a strongly activating group. That means, according to the previous table, NH2 should be electron donating. NH2 should be increasing the electron density on benzene. Okay, so let's see if it can actually do it. Okay, so the first thing that we are going to worry about when it comes to NH2 is the resonance effect and inductive effect of aniline, okay, or NH2 group. So we are going to worry about both inductive effect and resonance effect. So inductive effect basically talks about the electronegativity of the two atoms and the polarization associated with it, right? So according to inductive effect, okay, nitrogen is more electronegative. Okay, so nitrogen electronegativity is greater than the electronegativity of carbon. Okay, and therefore this bond right here is polarized and nitrogen is winning the battle, so it becomes partially negative, carbon becomes partially positive. So according to the inductive effect, actually NH2 group is electron withdrawing. It is reducing the intensity of electrons on benzene. However, if you take a look at the resonance effect, the lone pair on nitrogen can be donated to benzene ring. Okay, and this basically will increase the electron density. This will basically increase the electron density on benzene. How? Let me show you how. Okay, so you can draw resonance structures and figure this one out. Okay, so if you draw resonance structures for aniline, okay, you will realize that it can increase the electron density on ortho or para positions of benzene. So you will generate a negative charge on ortho or para positions of benzene, which means benzene has more electron densities on ortho carbons and para carbons, right? So that is why NH2 is an orthopara director. It can increase the electron density specifically on ortho and para positions. It can specifically increase the electron density on ortho and para positions. And also, the other important thing is that, I mean, here's the thing. So inductive effect is a negative effect. Okay, inductive effect basically decrease the electron density on benzene. Okay, so it will decrease the electron density on benzene. So this is a deactivating effect. Okay, so inductive effect is deactivating, but resonance effect is increasing the electron density on benzene. So this is an activating. If it is increasing, it is activating. If it is decreasing the electron density, it is deactivating. All right, so one effect is activating the electrophilic aromatic substitution. The other effect, the inductive effect, is actually deactivating the electrophilic aromatic substitution. So you have two things to weigh around, but actually when it comes to aniline, resonance effect is much larger than the inductive effect. Okay, so resonance effect is much greater than the inductive effect, and therefore NH2 group is a much better activator and an ortho-para-director. Okay, so for this particular example, resonance effect is much greater than the inductive effect. So overall, it is an activator. All right, so let's do something. Let's take an example. Let's take the electrophilic aromatic substitution reaction as an example for aniline, and then look at their resonance structures, and then see if it is also going to help this reaction. Okay, so by now you should be very comfortable in determining how certain substituents are activators or directors, and how they are orthopara directors or meta directors. But in the next in the next few minutes, what we are going to discuss is that how certain substituents impact through the actual electrophilic aromatic substitution reaction. So let's say aniline is an orthopara director. So let's think about auto attack. That means you're substituting, or you are attacking the benzene electrons to an electrophile, and then you are adding an electrophile into an ortho position. So you are adding an electrophile into an ortho position, so we call it auto attack. Why? Because you are adding the electrophile to the ortho position. Of course, there is another hydrogen on this carbon as well. Okay, there is another hydrogen in this carbon as well. So you can draw the rhenium ion, and then you can draw 3 resonance structures or 4 resonance structures as given in here. So you might want to pause the video and see if you could actually draw these resonance structures, and then you can examine these resonance structures further and then see if they are stable. Okay, let's see if they are stable. So we know that auto attack should be good for aniline. Why? Because according to resonance effect, when we talk about resonance effect, we learned that aniline actually helps ortho and para attacks, right? And when we examine these 4 resonance structures, we also realize that the last resonance structure that you have here is actually relatively more stable, which means every carbon you have in this benzene ring has an electron octet, but carbons that you have in these resonance structures, they only have 3 bonds, so they only have 6 electrons, right? So they are positively charged carbons, so they only have 6 electrons. So therefore, in this particular resonance structure, every carbon gets 8 electrons, so the electron octet is complete. So this resonance structure is more stable, and it contributes more to the resonance hybrid. It contributes more towards the resonance hybrid. So similarly, you can look at the para attack. You will also have a more stable contributor resonance structure for the rhenium ion. Okay, and in here this calls para attack. Why? Because you are attaching the new electrophile. Into the para position. And then finally you also have meta attack. So aniline is not a meta director. That means there should be something wrong with this attack, right? So if you are attaching the incoming group to a meta position, there should be something wrong. And as you can see, if you attach the electrophile into the meta position, you no longer get a stable resonance contributor. That means these resonance structures are not that stable. Since you are not getting a very stable contributor or resonance structure, meta attack is not possible. Okay, so these are some extra details for you. And then now you know for sure that why ortho and para attack is favored for aniline and meta attack is not. All right, next we have orthopara directors and deactivators. Okay, so most common orthopara directors and deactivators are halogens. Okay, once again, when you have a orthopara director and a deactivator, you look at the resonance effect and inductive effect. Resonance effect and inductive effect. So in here, what happens is that since it is a deactivator, inductive effect should be more. Okay, so inductive effect should be more dominant. Okay, that is exactly what happens here. Inductive effect is more than resonance effect. Why? Because resonance effect increase the electron density on benzene, but inductive effect decrease the electron density on benzene. So since this is a deactivator, inductive effect should be more. So deactivating effect should be more. That is why it is a deactivator. And then I'm going to briefly show you the ortho attack and then the para attack. As you can see, you will still have relatively more stable contributors when it comes to ortho and para attack. So if you draw the meta attack, okay, if you draw the meta attack, you should not see a relatively stable contributor. I don't have it in this lecture, but I mean you should be able to draw meta attack and then realize that okay, you no longer have the relatively stable contributor for resonance structures. Okay, so once again guys, if it is a deactivator, it should decrease the electron density on benzene, which means benzene no longer feels like it is rich in electrons, so it will be hesitant to attack an electrophile. So this reaction will be unfavored. Okay, why? Because chlorine is pulling electrons, so benzene feels poor. All right, next up we have a meta director. Finally we have a meta director. So one of the most important things about meta directors is that they are electron withdrawing groups. Okay, so if you have an electron withdrawing group, they are basically pulling electrons from benzene. It is like an expensive wife, so pulling all the electrons from benzene. So benzene feels really poor. So benzene no longer wants to attack an electrophile, because you are poor. It is hard for you to donate to charity if you don't have money, right? So that is exactly what happens. And even if these whenever you have meta directors, electrophilic substitution reactions are highly unfavorable. But even if it happens, it will only happen from the meta position. So basically, when you take a look at ortho attack or para attack, you will always have a highly unstable contributor. So if you take a look at this resonance structure right here, you have a positive charge on the carbon that contains the electron withdrawing group. So this electron withdrawing group is pulling electrons from this carbon, and this carbon already has a positive charge. So that is a highly unfavorable situation. If you are going to have a positive charge, you expect the molecule to donate some electron densities onto the positive charge, so that the positive charge will be more favorable. But instead, when you have an electron withdrawing group, it is also pulling electrons from an already electron deficient carbon, which is this one. So therefore, this is highly unfavorable. Whenever you have a highly unfavorable contributor, this pathway will not take place. So ortho attack is highly unfavorable. Similarly, you can draw the meta attack and para attack. Once again, for para attack, that is also highly unfavorable. Why? Because you are getting a positive charge next to the electron withdrawing group, highly unstable. So this will also not happen. So para attack is also not possible. And meta attack, Meta attack could be possible, okay? If you really want to attach an electrophile to a benzene, then this can happen. But in here, you no longer have an highly unstable contributor, but you also don't have a highly stable contributor. Okay, so since you also don't have a highly unstable contributor and a stable contributor, it's like, it is okay to get another electrophile, but it is not, favorable, so it is not activating. Okay, it is not activating. With that, I'm going to conclude this lesson. Okay, and then if you have any questions, guys, please let me know. Okay, all right, I hope that you guys learned something new, and we will be discussing some examples in more detail in a later video. You guys have a good one. Take care.